Okay, we just gave people a couple minutes to come in. What you can do if you want, you can upgrade your toolbox. Remember, you can use that the code you can find from the quick installation, and make sure you're in the right folder. I hope I was in the right folder. Okay, in the Teams channel, and that's what we are going to do. We have an agenda here. Jakarta is going to show us some of this demonstration because he talked about the neural networks, and I assume he's going to give some examples. And also after that, I can work through the framework of neural network, deep neural network provided by MATLAB, the toolbox. Then we will look at using example dataset. This built-in dataset is called patients. We will look at this MATLAB app called Classification Learner. So this is interface allow you to access a lot of the classifiers predefined in MATLAB. So you have a user interface as long as you know how to organize your input dataset and which is the input variables, which is the response variable you want to predict for. Then you define this X, Y, and then you can use the classification learner. The next, after that, I believe we need to get familiar with how, if you have two data sets you want to compare, basically you independently process two data sets and get this SCE variable, and you save to SCE1, SCE2. So we need to learn how to merge them in order to be ready to compare. So one may be from Y type and two from a knockout, for example, the treatment group. So after that, we will look at how can we annotate cell type using your own defined marker gene database. Because right now you click and automatically the program will use PangolDB marker gene database to annotate your cells. PangolDB provides 148 different cell types predefined. Basically, those database marker genes are from literatures and from user inputs. But you can define your own marker gene database. I show you how can you use that. If we still have time at the end, I will show you how to set up Python, the environment, because some of the function in the toolbox also majority, say 99% are developed in MATLAB, but some of the function I just call Python libraries. So in that case, you can expand the functionality of the toolbox to call external function writing in other languages. So we need to install Python in this machine. So you can just call that function and get back the results to display on your screen. Okay. Jakarta, are you going to come here and to show us?
So, hello everyone. In the last lecture, I just talked to you about the neural networks from beginning and the end and the future, basically. So I prepared some examples for you. First of all, I will demonstrate what is perceptron and the bottleneck of perceptrons back then. I've told you with the XOR problem. I will demonstrate all of them and and talk about how do we train neural networks and what are the parameters for setting the proper design or the combination, I can say. So let's start with the perceptron. I will just simply run this code. I will share this code in the Teams, by the way, if you would like to look for them and play with them. So when we start to train, we see there is a neural network training window. So as we can see, the epoch means the iteration. So we have to set some parameters like these training in this training process. We can call them stopping parameters. So we have to satisfy one of them at least to end the training. It can be an epoch number. When it hit the maximum number, it can stop. Or we can set a time until the training process finish. Or we can set the performance. So either one of them can be satisfied at the end and end the training process. The best option is performance, basically. So when we set the performance to 0, it means our error is 0 at the end of training. It's a beautiful solution. We want that every time, but it's not happening. You will see. So at this time, the epoch number ended our training process because it won't be able to fit the task we have given. So as you remember, we have this. There should be another. Yeah. Okay. This is what we call the XOR problem. There's a two class, the pluses and the circles. So it's impossible to classify them with a single linear line. So the single classifier as a perceptron can only draw a single line to classify any data. So as you can see, it's impossible for it to complete this task because our network is only consists of one neuron, and as you can see, the two input represent the x and y coordinates. It just multiply with the weights, and we add the bias at the end, and with the threshold function, we just produce our output. This output represents the line that we are seeing in here. So it didn't do the job. It cannot. So this is the main point that criticized back then and make some guys to write a book to have the potential is so limited. But it was all about the bad design and generalization of the perceptrons. Because you will see when we add multiple neurons, it will become so easy to solve any problem. So let's proceed. This is another example. I will just simply run it. So when our problems are suitable for the perceptrons, it can be easily solved with multiple lines. But it's all depend on the allocation of the multi-classes. So there's 4 classes. We just assign them at the coordinate system properly to be able to solve by the perceptrons with the multiple neurons. So as we can see here, there's now 2 neurons and 2 outputs, which will be able to draw us 2 lines, and these 2 lines successfully classify our data. When we look at our outputs, you see this ANS means the performance, the error of the perceptron in the training process. It starts with 8, then 4, and 0. So this time, our training process ended with satisfying the error criteria. So the output is here, the output matrix or vector and this is the target. So when they fit exactly or so similar, it means the training process is done and it was so successful. But there's a catch in here. If you remember that I said we have to define our targets in the coordinate system properly. So when we just shift it and run it again, we will see something not good. Okay, this is the bottleneck and the main problem of the perceptron, as I've been telling you. It can never draw this line, even though we have 4 classes, but the alignment is similar to XOR. So it cannot properly classify them, and as you can see, the error is never going to reach to the 0. So at the end, it will be stopped and fail. So we don't want to wait for it. All right. And maybe you can dig down, to solve, to understand why it's not working. The previous code block is working. I will shift it out for you, and I will be sharing this code if you want to, investigate it. So let's proceed. Okay, this is the main thing we will have some time on. So in here, we will be seeing that we moved from the perceptron. Now we call multi-layer perceptron. So we add an extra layer. So this layer is called hidden layer. This is the layer we added. So when we add a hidden layer, instead of just an input and output, when we add that, it will become MLP. So MLP is multi-layer perceptron. So what we call the architecture is something like that. All the neurons in each layer are connected. So this is the basic form. They don't have to be connected, but the most basic form, and it's like a standard versions of each class of neural networks. So when we connect them all together, we can call it basically feed-forward neural network. So the main title and main type is multi-layer perceptron. Whenever we have at least one hidden layer, it's a multi-layer perceptron. But we can specialize it with another properties. When we connect all of them all together, and the information is flow from input to output layer, as you can see, there is no loops or backward connections. This will be a different kind of special kind of type of neural networks. I will be telling you in a little bit. So this is the feed-forward neural network. This is feed-forward NN, but we simply say FFN, FFNN. You can see if you search some papers in the web, you can see the shortcut. So basically, the feed-forward neural network is a multi-layer perceptron. Multi-layer perceptron is extra layered and multiple neuron perceptron. So this is basically it. So why I'm telling you? So when we shifted to feed-forward neural networks with the special kind of multi-layer perceptron, let's set our neuron number as 2. But we remain to use perceptron properties, like activation function as a hard limb. It is a threshold function we just used. And train C is the parameter for the perceptron learning. So even though we advanced our architecture, when we remain the same properties as a learning function or learning rule and activation function, we still have some problems. That problem is led the what we call the winter of AI. So let me run this code. With only 2 neurons, let's see what we can do. By the way, we're still trying to solve the XOR problem. I'm pretty sure that it will hit the maximum epoch right now too, because it's so challenging for it with this setup. Okay, that is good. So it was so easy. It's not that easy every time because we have to run it multiple times. But as you can see, it successfully drew a 2 line to separate the 2 classes. So this is basically perceptron. We just used a little bit advanced form of the architecture. So with this little improvement, we can solve the XOR problem. This is our network. Okay, I can see the eraser. Simply our neuron is simply that. That simple setup can solve the XOR. But we cannot trust any machine learning algorithm with only one run. So this is the thing. So we try to approximate a function, basically. So we have to run it multiple times to trust it. So it cannot be a coincidence. We are not doing an exact classical method or parametric method. So let me try another time. And also there is an improvement because the window of improvement, because as you can see, we satisfied the epoch, maximum epoch number last time. There wasn't any performance improvement. So we couldn't reach the error of 0. We were so close, but as you can see, it never reached the error. So, oh my God, it did again. So it took me like minimum 10 times to see this scene when I'm preparing the examples. Can I run it one more time? So normally when you propose a method or try to publish anything or create, you have to make this trial like 1,000 times to convince it's really working with different setup of different parameters. But we are working with this so simple design right here. Okay. Do it wrong this time, please. No? Yes, it did again. So it's like ruining my plan in here. Just one more time. It all depends on the initial weights, by the way. Let me talk. 1, 2, 1, 1. 1, 2. This is 2, 1, and 2, 2. So we all want to reach the optimal value of each weights in this training process. What we are doing is updating these ones according to our error at the end, as I've been told in the Tuesday. So whenever we find the best optimal or best too close to optimal, so we will end up to see a successful predictions. Okay, it did again. So sorry, I couldn't make it fail for you, but it's not working like this every time. Believe me, it will fail a lot of time. It's just coincidence because the initialization of these weights are started randomly at each time when I hit the button and training process starts. These weights initialized randomly. So when you are lucky and it started with a good solution space. Okay, good point. I forget it. So it is our solution space. The shape is not convex, not linear, anything at all. So it's like an unknown area. So we just, when we initialize each weights, the problems start somewhere around, like let's say in here. So these are, let's say, our optimums, but there's so many gaps and traps in the solution space. So whenever, it's just all about where you start. So if you're lucky, your start point with the initialized weights will be near an optimum. So this is the coincidence. So in order to avoid this coincidence, we have to run it all over again 1,000 times. But this time, I won't pursue that. OK. Let's proceed. With the backpropagation algorithm, we just, as I maybe remember, they introduced a new and more intelligent training function with the more intelligent and really soft nonlinear form of activation functions. So let us see when we change them, what will happen. So when I change hard limb to, let's say, tangent sigmoid and run it, we will see the shape instantly, how it changes. And maybe a little bit more improvement. But I'm not sure. I'm not giving you any promise. I believe it will hit the epoch number again. No performance-wise any improvement. Yes. As you can see, when we change our activation function, yes, OK, this time I succeed. When we look at the actual outputs and the targets, it should be the same if it succeeded. So it didn't succeed this time, thank God. So it should be produced 0 instead of 1.5, and the same as gone like this one. So it failed. It should have been failed more at the previous setup, but let us see. But there's an improvement. You can see there is no hard edges because we shifted our mapping function. Like activation function is like a mapping, and it's a nonlinear mapping basically. So we don't have any hard edges right now anymore. I mean, we will have very soft and easy to adapt the real world nonlinear type of problem. So it will become blurry. That's what we wanted. So let's proceed and change one more thing to make it a proper multilayer perceptron. Our training function. TrainLM is basically a backpropagation algorithm. It uses the same error, but relies on the gradient descent algorithm and the derivatives, and it's more intelligent, basically. So let me run. And also, by the way, don't forget, we still have just 2 neurons. Let me run it. All right, we have a different window right now. Yes. So this time, it just runs 4 iterations. In just 4 epoch, it can satisfy the gradient. So it reaches the minimum gradient. What does it mean? So when we use our error in the form of sum of squares, it's just something like this. This is the representation of a curve. So when it does it, just in 4 iteration, it just started somewhere around here maybe and jump with the help of the DE to DWIs, IJs, this W. So it just propagate the errors, and then it just started to, jump all the way through. So 1, 2, 3, and 4. At the 4th iteration, it just easily found the optimum. So this optimum is satisfied our stopping criteria over here. So what we can see with the proper activation function, nonlinear activation function as a sigmoid function, we see this beautiful plot. So let us see our outputs. Right, precisely, right? It's like basically 0. The error is 0, basically. It's just precisely can classify it, and no matter I run it like thousands of times, depend on my experience, it will give you this in a very, very short time, because now it's really capable of and so intelligent. So let me try another thing. So what will happen if I pursue the previous setup, like remain in the perceptron and increase our number of neurons? So what will we see? I'm so curious right now. By the way, anyone can hear me? I don't know if it's working or not, but we are cool, I guess. Okay. I need to go there. Yeah. Now we can see, okay, well, I'm here. It's 10 neuron right now. We still have a hidden layer, but we are in the setup of the perceptrons still, the properties, I mean. When we look at that, okay, it seems, just a minute, yeah, it did a good thing, but we still in the hard zone, as you can see. Only lines it can draw, multiple lines, but there is no nonlinear capability of any mapping or any relationship that it can learn. It's still a linear form. It's the main disadvantage of perceptron. It cannot go beyond that. So let's do one more time. So what will happen when I use proper neural network, I mean the feedforward neural network with the proper updated parameters with 10 neurons right now? Let us see what we will end up. Yeah, as I think. Only 3 epoch, as you can see. I will shift the windows again. You know, our solution space is, in our solution space, it just creates so many better zones because it's now more advanced form. And it can create very good, points that successfully classify. So there's only 4 points. But when we increase that number of observations, this particular neural network with advanced form, with the multiple neurons, will act better every time. So now we have a successful neural network right now. Let us proceed. Okay. And sorry for that. I couldn't have time to translate the Turkish notes. Okay. This also the similar type of problem. We still have. Yeah. Okay, that's good. So these are our outputs, and as you can see, it failed. We have 2 class still, but it just failed because let us see what we have used as a parameter. It's all about choosing the parameters. Yes. As I said, when we increase the number of observations, the coordinate system is becoming so challenging to train for a particular neural network. So what we did just with 2 neurons, with the default parameters, you cannot see any activation function or training function parameter in here because its default version, it uses sigmoid function and the backpropagation algorithm. I just don't want to mess with them. I just want to increase our neuron number. And let's see what will happen. Yeah. All right. As you can see, even with just adding more neurons, it will now capable of successfully do the classification when it's challenging. So as we can see, it just classify precisely this time. So another trial in here. I will just increase that to 20. So let's see. It's a messy right now. It will become similar to single cell data, I guess, but we were far from it. But as we can see, even though it's really challenging, it somehow managed to successfully classify all the points, because there is no area that trap us inside, like cluster manner. I mean, it has to be in the, like, say, it shouldn't act like the clustering manner algorithm, like try to squeeze the data or make a, make a line around them. It just is free with the activation function. It can create any area that it can accomplish the task. So there's no boundaries, I mean. So just adding the neuron number, we did the job. So these are the hyperparameters. I mean, the neuron numbers, the activation function selection, the learning algorithm selection. There's tons of choice you got. But within time, you got the experience that you understand what needs to be done. I mean, to finding the proper selection of the parameter design. So let me proceed. I'm sorry, I have to close this mess. All right. Now I will talk. I want to talk a little bit about my special function. It's a really primitive kind of a special function that I've been used and published with an article back then. It's like a little toolbox of Dr. Tsai, but it's really basic form. It's just a nested function, specialized function, and it basically allows you to just run the experiment design. So in neural networks, as I said, you have to try many more times with a different combination of hyperparameters in order to achieve the trained network with the minimum error as it can be. So this is all it does. With the default parameters, it just uses particularly for time series forecasting, by the way. So input number means the legs of any vector. So in time series analysis or forecasting, we just use the past values of any vector of anything. As you can see, it's like let's give an example, like financial, like daily basis exchange rate or stock market value of any company. So when you got that data, it will be seeming like a time axis with the x observation. Let's call it basically observation. So what you will see is just something like that, change during time. So what we do to forecast the past values after that point, we just use these past values and we call them legs. So one leg means my next prediction based on the last day. And let's say leg 10. Leg 10 means I grab last 10 days observation basically to predict the next day. It's called one step ahead. One step ahead forecasting. So this is what's basically time series forecasting. You use the past values because in theoretically these vector has a property that we call autocorrelation. Autocorrelation means it just have some relationship within. So we don't have to provide or unveil this relationship in the neural networks because it's kind of a black box. You just feed it and it learns the data, the behavior, and how it relationship with past values, and then it just learn it. It becomes the experience of the data itself. So it can produce the predictions of what we call forecast because it will be a future predictions. And it will just make us its prediction how it will be ended up in the future. So basically, let me run a simple code. Yes, this is a sample code I added. Let me plot it. So it's basically, okay, sorry for that. Okay, this is basically a single line is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 100. So we use that data from 1 to 100, and we will expect from neural networks to forecast 10 or 20 step ahead forecasting. So what do you think when we train a network with a vector going from 1 to 100 and, like, say, 10 step ahead forecasting? So what should we expect to see at the end? The forecast will be naturally like 101 for the first one, right? So go for it. So if you are lucky, because it's a really long time to forecast, to keep forecasting, because 1 or 2 step is okay. But imagine you use past 10 years data, or let's say, okay, past 100 days of data of anything you can imagine, and try to predict the 10 more days ahead. So when we extend this forecasting range, it will become so challenging and hard for it to maintain that power. So I'm talking too much. Let's run it. I'm pretty sure it's running. Yes, it's busy. It's running. I probably, let me look. Yes. I just set the parameter for the window of the training process to 0 in order to increase the performance. But, all right, I'm sorry. Okay. It started. It will run exactly 100 times because I set the default parameter of input layer and hidden layer as a 1 to 10. What I mean, so number of neurons. Number of neurons. In input layer, it's 1 to 10. In hidden layer, it's also 1 to 10. It's a basic design. So you shouldn't have to tend to it. You can increase it to, let's say, 1 to 20 or 10 to 20. It's all up to your data and your experiment. So, and for the hidden layer also, you can increase that 1 to 10 or 1 to 20 or 10 to 12. So sometimes we can already know at the beginning that 1 to 10 hidden neuron, it won't do anything because your data is so challenging. So basically in the CBNet parameter, you can set just, okay, minimum hidden number set to 10. Just start from 10 to 20. Or you can add the second hidden layer, which will become something like deep network that will be calling, but it's simply not. Deep networks is much more advanced and complex form. So just adding second hidden layer, it won't make it any deep network. So the same thing going on in here. And at the output layer of the number of neurons, we only have one neuron because what we do, we use all this past data to predict only one data. So this kind of design should be remind you something, some specific type of analyze type. It's a regression basically. So we just use the multiple data in order to predict single one. But at a time, at the time of the training process, it just produced one prediction, but it can be multiple times. So I'm not meaning that it's only capable of predict only one prediction. This is just a design. It's about to end. So any questions so far? I'm just keep talking and talking. Any? I also got some funny stuff too after that. Oh.
So you feel that you have to do this answer the
Yes, yes. It's basically the architecture one. It just started with this architecture. One neuron in the input layer, one neuron in the hidden layer, and one neuron in the output layer. So it goes on like 1, 2, 1, 1, 3, 1, up to 1, 10, 1. And it shifted to 2 neuron in the input. That means it started to use 2 lag. So 2, 1, 1, 2, 2, 1, all the way down to 10, 1. So 10 in here, 10 in here, and my hyperparameter for input layer number is 10. So basically, our last architecture to train is 10, 10, 1. So it become a 100 neural network to train, and it will. It's about to finish. I just want to show you what's about training a neural network in a proper way, in a proper parameter design. The parameter, by that I mean the hyperparameter. So neuron numbers, activation function selection, learning parameter selection. These are all the parameters you have to assign. So you will build an experience in time to choose the proper ones. I can set the proper design in just one architecture. I know, but in order to show how this algorithm works, how this function works, I just have to run for you. But it's not that hard every time. In meanwhile, you just get the intuition that somehow you just find the proper parameter design to try. Okay, it's finished. Let's stop talking. And also this algorithm is capable of using different kind of, let's say, criteria. What we call as a performance criteria is like RMSE, root mean square error, is the well-known, widely used. It's just a way to measure the error. So we measure our error based on RMSE, and we find that our best error is this, and this architecture provides us this particular performance. So, but when we use so complex form of data and a different kind of performance measures, it will change. So what I mean that root mean square error handles the error or calculates the error in its own manner. So when you use mean absolute error, this is a different kind of a performance measure. It can be choose different architectures. So at the end, choosing a proper performance criterion is also a hyperparameter. It becomes a hyperparameter to choose because it will end up giving you different architecture to make your predictions in the future with the new data. So it finished. 10, 10, 1 is giving the best. So just a little visualization for you. I prepared a more complex one, but it appeared that we don't have a time. But sorry. Okay. What we are seeing is that our training part of the data is blue, and the red one is forecast. So it's exactly what we wanted. It learned the behavior of the data. Even though it's so simple, it can learn so much complex forms. I can show you, but later on, because it will take training time so much, I planned to show you. And just, okay, these are the all results you got after everything's finished, the array. And when you choose the proper line, okay, this is our forecast. So it just precisely forecasted 10 step ahead forecast very beautifully. So for the 1 step ahead is 101, 2, 3, and 4. So it based on, when it forecasts the first step ahead, so the input shifted to this point. So for this forecast, it uses the last 10 observation of the original data. When it produces it, the window is shifted. So it will use the forecasted ones to forecast future steps. So when it come in here, it just uses 9 forecast and 1 last observation of original data to predict the 10th one. So when you set the step ahead parameter to 20, 30, 40, it will become so challenging because of this one. So it has to forecast so precisely, so good in order to maintain that performance in time. So it's a really difficult task, but it can be done. As you can see, I believe that if I set this to 50 instead of 10, it will be doing this job so beautifully because it learned so beautifully, so good, and the data is so simple. That's the case. So any question? All right. So I want to shift to convolutional neural network so fast. I just want to run it. It's because of time. I'm so bad at time management, so I'm sorry for that. I've planned to show I can talk like hours and hours for you. Okay, let me check the error. So convolutional neural networks, as you remember, it's a special neural networks to use for image recognition. So this time, instead of the numbers, we just have our pictures. What we call this kind of images is so well known. It's so famous. It's MNIST. You can find anywhere in the web. So it consists of numbers. I mean, not the numbers. These are I don't know how to call in English. Like, sorry. No. I mean, it's just 0 to 9. So there is no 2-digit numbers. Okay, but you can combine it to produce. This basically 1,000 0 and 1,005, 1,009. So this data set consists of 1,000 of each number with different position and different size. So this is like an XOR problem in the perceptron. For image recognition, when you come up with some algorithm, you have to prove it with this MNIST data set. So when you successfully prove your method with this data set, it just means that, okay, it's ready to publish or ready to use by another people. So, okay, this is our training process. As we can see, it just runs so perfectly and so fast. This is the loss function. As you can see, it just degrades over time. This is our gradient. So this should be like close to 0. It should end up like it did. But maybe you can see there's some jumps over there. So it's not going smoothly. It's a crucial point to train a network, because what is here we call is regularization, some kind of regularization. So what it means, it just make it hard for neural networks to learn so easily. It creates challenge in the training process by doing some strategies, doing some tricks, like cut off a neuron in the training process. Let's say in the convolutional neural networks, we got tons of neurons in so many layers. It goes and on and on. So when it's learning, imagine that, okay, this regularization, do that. Let's cut these neurons randomly. Let's cut this one too. And see if it can still proceed training process. So it becomes a challenge to make it learn so properly and can be generalized form. So this is the accuracy. This is the loss function. As you can see, it's 99%. It reaches so fast, only 48 seconds. So now it can learn. I mean, it can predict any number given from the MNIST data set. So this particular one, yes, I chosen 4. Let's say it gives the true or not. Okay, as you can see, it's because it starts from 0. This is the 0 class. So it's these are the probabilities, by the way. So the prediction belong to 0 class with the probability of nearly 0. So that means it's for 99%, like not percent, 99 of probability. It just classified as a 4. So I just feed the network with the image of 4, and it gives me, okay, this is 4. Let me show you again. Yes. After training, I just feed the network. I just give the example. Okay, let me classify this one. So it classified at the 5th class, which is for 4, number 4. So this is basically it. Can I be late like 5 minutes, sir? Is it okay to extend like 4 or 5 minutes? So this is the convolutional networks. I will be talking so fast with the. Okay, maybe you probably asking that how network can use images as an input. So in these lines, it just read the image and convert to the pixels. So 28 by 28. It's just accepting form or format of the matrix. So it just basically say that, okay, there's a 2D image, like not a complex, this 2D simple, very low resolution, 28 by 28 pixels means the matrix size. So each cell corresponds a pixel value. So let me show you really. So let me undock it. So this is what 28 by 28. Can you guess which number is that? So it's what actually convolutional neural network sees as an input. This is the input. So let me just run it like a plotted. Okay, it's 4. It's what we it's what we just feed the neural network. It's actually 4, but it's not like how how we see. It's just how it works in the pixel format in the pixel matrix. It's that easy, but basically, just when you have high resolution data like 1,000 to 1, it can be a very complex form of the image, not like low resolution. It can be 3D. And you just add layers after it, and it just that. So I was so curious when I was first learning what's convolutional networks, how it reads the image. It's that simple. It's just all the problem is how you define your input, no matter it's text or image or anything else. Convert somehow meaningful data set, meaningful matrix format. So after that, you just give to the neural network, and it do the job. Yeah, matrix is matrix is the key. Matrix multiplication, as Dr. Kai said, is everything. You just have to know your way to convert it in that form and how to use it in this multiplication adding kind of process. So after that, you just understand so well what's happening over there and here. So the last thing not last, but this is the LSTM. LSTM is working is for especially for text-related classification or generative tasks for AI. I don't want to run it so long, so I will just set max epoch to maybe just 3, and because as you can see in here, I did the proper set of 300. Can you see that? So, okay, I'm sorry. It's just epoch number set to 300, and it took 7 to 8 minutes to alone train it. It's just 100 neuron. But the LSTM neuron is so complex form, so it just creates so many challenges to the training process. As you can see, there's so many calculations, so many epochs runnings, and the accuracy is dropping down and up, down and up. So it just, but at the end, it just learned this one and produced the new text after it. So let me just. Okay, this is the actual text. It just get from the web. It's Alice in the Wonderworld. It's just a script or the book writing. So basically, we feed it with any text we want. So let me. sometimes it uses so many toolboxes and files, so it can sometimes confuse. Okay. It read last time, but no this time. So, okay, when we, after 7 to 8 minutes, in the 300 epoch, it learned the Alice Wonder World. So it just read everything, and it learned everything in it. So it just started to produce, like I say, give 500 word or property, because the blanks also, how do you say, blanks? No blanks, just spaces are also a prediction in here. So everything you see is just generated purely from LSTM. It's not exist, it's not written text. So it just, after it read the Alice Wonder World, it just produced this one. So I don't remember, I read it years and years ago. So maybe there's some meaningful things in here, like Mock Turtle, do something with the king and queen or something like that. But we have to catch the, the properties of the sentences, and the words come after it. So it just makes sense. It's just properly designed. It's just not the nonsense of blah, blah, or blah, blah. So if the predictions make any sense, it means it's creating something like successful. So as I told you in my previous presentation, there's some short films just shoot it like a script based on the LSTMs. So it's that powerful. So my final thing will be a little demonstration. I'm so late. I'm sorry for that. It was okay. It's here. So with just like 10 lines of code, you can do something like that. I just connect my camera to MATLAB. You can do that. But before, let me close all. Okay. So I will connect to AlexNet. So this is this AlexNet is the one of its first kind. So back in 2012, the first the huge convolutional neural networks with thousands of images are trained, and it just sits in the web, in the cloud. It's somewhere in the somewhere, I don't know. But it started the way of AI is going, because it can take so much time and effort to train this large kind of neural networks. So back then, it started with the AlexNet. It's 2012, I guess. They just created a network, and they just provide for public. So it's just like, okay, we trained this huge network. You just use it whenever you like to. So this is what we are going to do right now. We just connect to AlexNet. So our NNet is now AlexNet. So when I run this while loop, okay. Sorry. I'm so bad at, okay. You see the label? It just perfectly, and yeah. I also bring some items with me. Let me try. It can. Okay. Oh, no. Yeah. It catched. So it's definitely not a proper way to feed the neural network, but yeah, matchstick, something like that. Matchstick. I don't know. It's not matchstick, but let me grab something. I just bring some banana. Yeah. Come on. Green snake, something like that. If it's yellow, it will catch bananas so easily. But as I can say, it's just not a proper way. Okay.
Just gas.
This is yeah, it's just gas. But let me. Okay. Toy of my kid. Yeah. Toy puddle. Yeah, it's good. Okay. What else we got? Okay. What about the water bottle? Yeah, I see that. You see that? Pop bottle? No, it was, yes, water bottle. You see? So, anything else? Yeah. Sorry? Ah. It can definitely do that. So, yes, tennis ball. And finally, let me, yeah, it's a ping pong ball. I still the goldfish now. Orange, hey, yeah, I see. Did you catch? So it's not a proper way, but it knows thousands and thousands of images. So if you feed it properly, it can produce you anything you want. And also it can be upgradable. So when you yeah, sure. I was so, yes, sweet, no? Okay, maybe, sir, no, what is it? Okay. Yes, because there's too many things. Like there is a class of thousands and thousands of vector, and there's a probability mass. It just tries to pick the most probable one out of this huge vector of probability. So basically, we can do labeling, and there is a catching in your phone. It just detects your face or something like that. So it can be advanced. When you write some lines of codes with capturing the any object. So we can do that. When you do that, it just stabilize the input as an image form, and it will become more precise that time. So, but I didn't have any time to extend the code. I also make it took so much, so I'm sorry for that. So that's basically all. It's what neural networks can do in a little example. There's so many things going on, so it's better to understand and learn how to use it basically, not to create it, because nowadays they become so complex, so advanced form. Even though understanding is for me like an expert is like really hard task. So I just recommend you to use prompting and how to use the AI instead of creating it. But it's just basically that. So this neural networks became an AI. So every time you see that, you just remember there's some neurons connecting each other and create this. So that's all. I'm sorry for taking so long, but I wanted to share so much. Okay. Thank you. Sure. Yeah. Everybody can try it.
Okay, now we are moving on to next topic. So we will look at this built-in app in MATLAB. First, we will load example data. If you want to copy these 3 lines of code here, and just copy here. Okay. So we just prepare our input data given to the classifier. So this is a pre-provided data file. It contains several variables, okay, in different names. So diastolic, systolic, this blood pressure, height, age. So we put those 5 example variables in a combined. So we combine them together. These 5 different variables into X. And then we want to predict the gender. Okay. So we will use information collected in big X matrix to predict the label in the Y. So if you look at the Y, this is just a list, okay? Male, female, 100. And in X, you also have a corresponding 100 samples. And then 5 columns of variables: age, diastolic, height, systolic, weight. So we are going to use this information to predict each label. This is the training data. We are going to use this to train the classifier, to let this to be ready to predict in future. If you give 5 numbers, they will give you a label male, female. Is that clear? Okay, so this is a very typical classification problem. We're not going to start from scratch. You can start from scratch if you know these command lines. But here, if you click these apps here, okay, this tab, and then you have this drop-down menu, and then in machine learning, I clicked. Yeah, right here, okay? Can you see it? Yeah, so if you're ready, just click that. This will bring up this interface. There are other learners or neural network designer, but we are going to use this very classic, okay, classification learner. Once we start this app, and then you click a session, and you want to import your training data from a workspace, because we are ready. We prepared X and Y. So here you select where the dataset variable come from. So we can select X. Okay. And then you will select a variable from a workspace here. And we want to predict y. Okay, is that clear? So we prepared a table, X table, contains 100 samples with 5 variables, and gave this program as a data set. And we want to predict response variable, which is y. It's just a label, male, female. Then we are ready to do this training and see, I want to have cross-validation 5 times, 5-fold. So you can increase this or decrease this, and you can start the session because we are ready. So in this tab, there are some summary statistics. Their scatter plot depends on which 2 variables you use. You bring height, weight, and those labels are the male, female labels because you have 2 clusters, 2 groups indicated differently. Yeah. Then you can start to select your favorite classification methods. It's in here, so it's called a model. Okay, depends on which model, which algorithm you want to use. You can select Gaussian, Bayes, linear LDA, linear SVM. Okay. KNN, different flavors of KNN. KNN means K is a number, how many neighbors, nearest neighbor. Okay, that's algorithms. All for small data set, you can run them all, right? So here we just select what we discussed in the lecture. So this is a decision tree. We probably will delete that. I will keep linear description analysis. I will keep Gaussian. I will select find KNN. So those are the algorithms we mentioned in Tuesday's lecture. So I just keep 3 of them. And then after select them, I can run those training model. Okay, for this small project, it's very easy to build this model to train, to change the parameter internally, and then look at the performance, the accuracy by using this cross-validation. So linear discriminant analysis gave you 100% accuracy. So 53 males have been classified correctly into this group male, 47 of them, there's no error. So this confusion matrix look perfect. But if you look at the KNN model, there 2 has been misclassified. The true classification should be male, but the algorithm gave 2 of them become female, become male. So there are 2 numbers here, okay? There's nothing wrong with this here. So that's the way you can try different model, different algorithm, and then once you finish, you can see, okay, I want to export this model. So you can save the trained name of algorithm and with this parameter. Save to the workspace and become a function. This function will take 5 numbers and give you a label. So you can use that to get new input data to do the prediction. That's all. All right? So you just need to know how to organize your input matrix using what variables to predict what responsible variables. That's all. Responsible variables should be the categories. Should be 0, 1, maybe 1, 2, 3. In this case, it's a label, male, female, because this is a classification problem. So we do this categorical variables. Okay. Any questions? Is that okay? So I hope you can find applications in your future study once you have an Excel spreadsheet with a lot of samples. And you probably want to learn this relationship between your columns and the labels of samples using this method. Okay, we are going to move to next topic, is using toolbox. As you know, before we have ever tried, actually, you import 2 accession numbers from the geo database. You can have a GSM 1, 2, 3, 4, comma GSM 3, 4, 5, 6. Well, these 2 will automatically merge, and you import that. But it's okay. There's many different other ways you can make this. But once you have that data in there, you can save to the workspace. For example, I will create an empty, so SCE. So you know you can create a SCE object. So I created 1, so this single cell experiment. This will be empty. I just put that as an example. You have 2 your own. So you have 2. So for example, in workspace, you have 2 variables there. Then in the toolbox here, you can see I want to merge these 2 variables and make it one concatenated. So I still load this example data, but it just allow me to move to next step. So because you know how to prepare these 2 variables, if you know how to deal with individual data set, you can save this and that in the workspace. Now once you are ready to merge, you can select this edit and merge SCE variables, these 2 variables in workspace. You select that and select them, the data will be merged. So that's what I'm doing, okay? But this example, these 2 example data sets are empty, make no sense. But I just show you, if you have this SCE variables in the workspace, you just do this, okay, to merge them. It's empty, so it shouldn't work. Let's get it back to here. Then we load example raw data without annotation. Okay. Load example raw data, no annotation. But this data set has been prepared for you. Is the merged data. It contains 2 samples. So you can look at this batch ID and to start to see, okay, there are cells from 8 weeks and 14 weeks. 2 batches data, okay? As I said, we normally just run this embedding, okay? (3D) embedding with 2,000 highly variable genes. So I just do this embedding for all the cells, not independently for batch 1, batch 2. I just do them together. If they separate into different clusters, that's fine because they form 2 different conditions. Maybe they are separable, but some cell type will be still in the same cluster. That's fine. Okay, so remember next step is to do clustering. K-means using this embedded position of the cell instead of the whole matrix. We only embedded the cell using t-SNE 3D, so there's only one option here. So if you have tried UMAP or other methods, you have multiple selections here. Okay. Right now we only have done this, so there's only one embedding variables we can use. You select OK, and K-means this number is predefined, and you can change if you want to make more small clusters to make this number bigger, or make it smaller to make big clusters. But this predefined depends on the number of cells here. On average, we expect to have 100 cells in each small clusters. Using the clusters to this 100 cells to determine the cell type. Okay. Yeah, let's try. So I'm going to use a larger number, a small number clusters. I will recompute to put this into 15 different clusters because I want to do this manual selection. So I don't want to have 80 different selection. But if you use 80, then allow to do the automatic annotation. That's pretty good. But now I want to show you the manual annotation for each individual clusters. So I want to run 15 times this annotation. So I group them into 15 groups. Now I select assign cell type to groups. This tells you the algorithm, the data size, the data source, and the reference ID. And then this is the mouse data, so click mouse. Now you can select, remember you know how to do this alt annotation, but now I show you the manually. So if you say no, you will be asked for each cluster. So I have 15 clusters. I will be asked 15 times, what do you believe this cluster should be? Okay, so this is for cluster 1. The first pop-up window asks me the top option determined by the algorithm is endocrine cells. But if you believe it's delta cell, then you can select the second option. Or you believe they are interneurons, you can select this. So in this step, gave you some input from your understanding of your cell system, rather than automatically give the best algorithm options. So you can select. So if I think this hepatocyte, I can select this first cluster will be annotated as hepatocyte. Then the second option, this is for the second. Remember, I have 15 different clusters. This is my second. If I believe they are macrophage monocytes, I just randomly select renal cell, fibroblasts.
How do you know which one is class 1 and class 2?
Yes, I don't know yet, but yeah, you can label them with the numbers. Yeah, but for now it's jump from different colors. Yeah, I just select. So in my case, I have to decide 15 times because I have 15 different clusters. Yeah, at the end, the algorithm will ask whether you want to merge if you have these subclusters. Fibroblasts 9 and 11, their cluster 9 has been classified as a fibroblast, and the same as 11, whether you want to merge these two clusters. If you know, the algorithm will keep all the subscripts for the different clusters. Okay? So this gives you some flexibility to decide the cell type based on your understanding of the cell type you worked with, the tissue sample. Is that okay? Okay, good. Now we can label the cell by class ID. Just forget about the annotation. I just put that in. So this is class ID. We run through 1, 2, 3, 4. Okay. But now I want to show you if I have my own marker gene database. I don't want to use it built-in. Then you can select edit. Then let me see where it is. It should be in tool, annotate. Okay. So what we have just done was to use this to annotate based on the PanGLODB provided marker gene database. But now you have a chance to give the input of your own marker gene database. So you select this. So I prepared a marker gene list from another database called SC type. If you don't want to put your own, you can select, see here, you can select, okay? So for now, I just say no, because I want to show you from completely customized cell type database. Okay. Yeah, I try a different way. To annotation. No, I will put my own. Okay. So this is something you have to input for your customized database. You need a cell type name. So here, the example, I just put cell type 1. And then you need a tab, okay? This invisible here, but you need to have a tab. And then you put your list of marker genes. You believe, okay, those genes should be the marker genes for cell type 1. Those genes should be separated by a comma here, okay? So you have and in this example, I have a cell type 2, and then tab. I have this random gene name in there. This is just an example that doesn't make any sense, because this gene list was randomly generated. But if you use this customized gene marker, you can start to predict. So you see, okay. And if you do manually, and the algorithm will still run, okay. But the output is only cell type 1 and cell type 2. That's based on your definition, okay. I only use those markers to tell me. And the algorithm decide, okay, those cells looks more like cell type 2, so I gave label this. Some are cell type 1, label that. And some is completely unknown. There's no gene expressed in this cluster of cells. No marker gene expressed at all, because I use a very small data set, the random data set. It doesn't make any sense. The same thing, okay? So you still merge, and there you customize the cell type annotation is here. So in this, I provide a more realistic example of customized database. So you can click this, and I hope you can select them all, copy, and put into that small dialog, okay, to replace your hypothetical annotation. So if you say no, this window, I cut this and paste the long list I just prepared. And let it run automatically. Let's do this clustering. Yeah, I need to label the cells with cluster ID. And then I can put in a customized database. Let the algorithm to decide the cell type for each cluster in there. Okay. Any questions? So you need to know how to prepare this, okay? The cell type and the genes. Put that into the correct format, paste into that dialog window. You should have this customized annotation of your cell type. You can name it whatever. The algorithm doesn't care, but you have to care yourself. Okay, what's on our agenda here? Let's close this. Okay, so next we move to install Python environment. So in this menu here, I incorporate several Python-based and also R-based programs. For example, the pseudo-time analysis using Monaco 3 is a very common approach. People try to build a pseudo-time, so I'd rather to call this package here, but we have to install. For example, I want to use data map plot, but there's a /py indicated this function require Python. If I click this right now, this function require 2D embedding. I have to prepare a 2D embedding for the algorithm first, and then to call that. So let's just do a 2D embedding. That's easy. So I will use Tisney and select 2D, prepare embedding for the algorithm. Okay, so this is my 2D. Then I see, okay, I want to try this, but now I need to select a working folder to put my temporary outputs. So I select, you can use a temporary folder or just select one of these document is fine. So I just select document. Now we run into the problem because I have no Python installed here. I will have to check set up a Python environment. Now the program try to find Python.exe executable program, which the Python environment. So I have to check where it is, but because I haven't installed it, there's no way I can find. So we are not ready, so not set. So how can we do that? So today we just install Python, and then getting ready, and then we are done for this week. Okay. So the version I want to install is called Mini Conda. Mini Conda. So Mini Conda is provide this Python environment for you. And we just found this installation, installing Mini Conda. This is for Windows. It's download installer. Okay, basically just like install any packages, other packages. You just download this installation file and just keep it run, click it run, and then install in your local account. That's all. It's just me because I want to install a local Mini Conda. So remember where you install it, okay? So because you want to find where it is later. So it's under user, my username, app data local Mini Conda. That's all. Okay, once it's finished, so I can provide this link to the channel. So install setup. So after installation, I come back to here and select setup Python environment, and I will search for that Python command. That's in user, my name. Looks like it's hidden. Yeah, so I have trouble to find it. Because this folder is invisible, so we have to somehow find it. So I switch to this folder, go into click Python here. Yeah, something wrong here, and I will come back next week and see what's happened here. Okay. But basically, you need to give the instruction to let the system know where this Python exe file is located. All right. Any questions? Okay. So I cannot set up Python environment on this machine today, but I will let you know what happened next week. Okay. All right. See you next Tuesday.